All right, today we're going to talk about complements, unions, and intersections. This is on section 13.2. It's around page 677 in your book. And we're going to talk a little bit about these type of things. So sometimes when we want to show the probability of an event happening, we're going to kind of label it this way. This is the probability the event occurs. And maybe the probability is 20% that something happens. So we usually write that as 0.20. We usually write it in decimal points. And the probability, what we're going to talk about is the complement of this. To show the complement of this, we put a little line right there. And this is the probability that this event doesn't happen. Okay? Or maybe we're recalculating it a different way. So this is the probability of the event most likely not happening. So if it's 20%, this would be 80%. These have to add up to 100%. So the probability of this event not happening would be 0.80, or that adds up to 1.00. So one way we could figure it out, let's say the probability of an event happening was 0.35. The probability that it does not happen, so maybe something else happens, would be 1.00 minus 0.35. In other words, we just subtracted from the total 100%, or from 1. And that would be what? That would give us 0.65. So that's the probability of something not happening. I'm going to move this down just a little bit. Right in my face. There we go. Okay. Nothing's working right now. All right. Let's see if we can do another thing here. Let's see if we can take a look at kind of an example. Example one in the book says, okay, they have this drawing right here that you can't see because I moved this out too far. Let's move this back a little bit. Okay, so you have this drawing, and this is like how people vote in the election. So many are Democrat, Republican, Green, Libertarian, other, and so on, and some are none. Okay, so what we want to figure out, what the question is, um, if we randomly select a person from this group, what is the probability that the person has a party affiliation? The person has a party affiliation. Well, one way we could do that is we could add up all these people that belong to political parties. So let me write that down. The people that belong to political parties would be, well, according to this, there were 37.1 were Republicans, Democrats, but we just put down this as a decimal. So when you have it as a percent, we kind of want to list it as a decimal. So we're going to write this as 0.371. We're going to move our decimal point over 2 places. And then there were some Republicans, and then there were some green something or other. I don't know what it is. This was 4.4%, so we're right at as 0.044. There were some libertarians, 0.035, and then there were other groups, 0.072, 7.2%. So each one of these, you could add them up as a percent too. I guess it wouldn't be so the end of the world or something, but we usually don't do that. I guess I should have written them down. So what we could do is we could add all these up. And if we add them up, I'm not going to spend a lot of time. It should come out to 0.6763. But a faster way would have been to say how many, we know how many are none of these, this area right here. So if we subtracted that from 100%, we would find out how many belong to political parties. We know that 23.7 belong to no political party. So let's change that to a decimal, 0.237, and let's subtract that from 1. 1 minus 0.237. Let's put that in our calculator. Clear this out. 1 minus 0.237 was 0.763, exactly the same number. And see, that would have been a lot faster than trying to add all these together. It's not wrong to add them. It's just that we're using the complement. So we could have written this as the complement of E, like this, of our experience, E meaning experiment. The complement of our experiment was 1 minus how many did not belong to any political party, and that would tell us how many belong to political parties. These are not parties. Therefore, this is parties. So just kind of a way of doing it that makes it a little bit easier. Okay, so that's what we mean by not belonging to a party. I think I had another problem here, but I think you get the idea. So here's another one, number 3 in your book on the exercises. It says there's one chance in 1,000 that you would win the lottery ticket. What is the probability you would not win it? The probability of not winning the ticket, having a winning ticket, is 1 minus the chance that you would, which is 1 in 1,000. So we have 1,000 over 1,000. 1,000 over 1,000 minus 1 is you have a 999 out of 100 out of 1,000 chances you will not win. Somebody's going to win, but you have the odds are totally against you winning it. Okay. Now, in probability, one other thing, if we're just using decimals and we're not using percents, the probability of it not happening, totally not happening, the probability it does not happen is 0. And the probability that it will happen, will automatically happen for you, is 1. And your probability is somewhere between these. It's between 0 and 1. Sometimes we show it like this mathematically, that X is between those two numbers. So maybe you have a 50% chance of winning. So your probability is 0.50 or 0.5. That's between 0 and 1. So probability of 0 means it's never going to happen. Probability of 1 means it's always going to happen. Okay, so that's what we're talking about there. Okay, the next kind of probability we're going to talk about, let's see if we can talk about some other things here. Some of these become kind of confusing when you do them. And in the book on 675, there's some formulas here, and these might be kind of confusing to you. So let's suppose that you're going to pick a face card from a deck of cards. Face card. Okay, so what kind of cards are face cards? This thing is not cooperating, or maybe it's just me. Let's turn it a little bit. Okay, face cards. Well, face cards are, aces are not face cards. Okay, face cards are cards that have pictures on them of a person. So we have a king, queen, we have a king of hearts, a king of diamonds, let's put a heart, king of diamonds, king of spades, and a king of clubs. Which kind of, I don't know what a club looks like, kind of like a funny looking thing like that. Okay, so you have these different sets. These two sets are black cards, and these are red cards. So you have a king of the hearts, diamonds, spades, and clubs. And you also have a queen of each one of these, and you also have a jack. So how many cards are there altogether? 4, 8, 12. There's 12 out of 52 cards that are face cards. And let's suppose that you wanted to pick what's the probability that you will pick either a face card or a red card? Well, half the deck is red and half the deck is black. So there's 52 cards in the deck, and half of them are going to be red, 26. So you might say, oh, my probability is 38 out of 52. We're going to add these together. Probability that it's a face card plus the probability it's a red card. And so you say, well, I have a 38 out of 52 chance of winning. But what happened here is that's not accurate because you double counted. Okay? You counted red face cards. You counted red face cards when you counted here. These were, you counted all the face cards, but then you counted again here because some of them were red. So this Jack, Queen, King, Jack, Queen, King of hearts and diamonds got counted in here, but they also got counted here. So what we have to do is we have to subtract off, and this is what we call an intersection. This would be the union of all the events, everything happening, but then we must subtract off the part that you double counted. You counted them twice. You counted them as a face card, then you counted them as a red card, and you can't do that. So we have to subtract off 6 out of 52. So the probability of this happening is really 32 out of 52. Now, sometimes when we have a problem like this, we reduce it, we cut it in half, we divide both of these by 2, and then we're divided by 2 again. So sometimes if it's left as a fraction, the probability is the number of successes over the number of failures. We have 8 successes out of 13. The probability of you drawing a face card or a red card at random would be 8 chances out of 13 that it would happen. Or you could change that to a decimal, 8 divided by 13. Usually in a situation like this, we leave it as a fraction, but you could change it and round it off. It'd be about 0.62. Okay, so it could be expressed as a decimal, although most of the time we want to leave it as a simple fraction. Even if you don't reduce it, it's not terrible. But so in the book, they kind of give you a formula, and this might have kind of thrown you off a little bit. So let me write this down. Okay, the probability of it being a face card, and the word or, we use a symbol like this is called a union symbol. Probability of a face card or a heart or a red card, we're going to write it like that. Fur, I guess it spells. I didn't really think about it. Probability of a face card, union, red card. That means or is equal to the probability. I'm going to put this back up here so you can see the probability that it was a face card. That would be your probability right there. Or the probability plus the probability it would be a heart. Minus the duplication that you counted them, the double counting. So we call that an intersection. We write it this way. It's going to be written as the probability of F intersect R. See? This is called an and And this is what we call an intersection. And this part is called a union. The union of all these things is the probability of it being a face card, probability of being what did I put in H, a red card. It should have been a red, minus the intersection, the double counting. This is where you double counted. And that's how we write that. An example would be, well, an example, they had one in a book here where they just used hearts. The probability that you picked a face card and then you picked a heart, but these cards are both hearts and face cards. So that's how they did it. Let's do that one. The probability of a face card and the probability of a heart, the union of that is equal to the probability of a face card. 12 out of 52. Let's get this straightened out. Plus the probability of a heart. Put a little heart in here. Probability of a heart. There's 13 hearts in the deck. We got face cards and aces and number cards. That looks like 25 out of 52 minus right here, as they show in the book, 3 of these cards are face cards, but they're also hearts. So we've got to subtract those off. And that's our intersection right here. So that's all they're saying is that you were double counting here and you've got to take that away. You could either take it away from the 12 or you could take it away from the 13, but you can't count twice. You can't, that would be not accurate. So 25 take away 3 would be 21. No, 25 take away 3 would be 22 out of 52. Okay, that makes a little more sense. And then they reduce this by 2, 11 out of 26. Okay, so that's all they're saying there, and it looks like it's all confusing. Let me give you another example here. Suppose, I'm going to give you one here. Suppose A and B are events. They're just events. Something that's happening. These would be events. Pulling a face card, pulling a heart, that's an event. Okay, and they give you some information. The probability of A coming up is 0.35. The probability of A union B is 0.65. The probability of A intersect B is 0.15. The probability of B is what you have to figure out. Now you're saying, oh my God, this thing is like totally confusing. Well, it is until we straighten it out. So what we're going to do is write our formula first. Formula like this one right here. The probability of the union, let's start with the union. Don't worry about these numbers yet. Is equal to the probability of A, first one, plus the probability of B, the second one, minus the probability of the intersection. Okay, so that's how we're going to write it out. Okay, that makes a little bit more sense, but not totally. So now we're going to put numbers in here. The probability of A union B is 0.65. The probability of A is 0.35. Plus the probability of B is 0.15. We know that's what we don't know, so let's put an X there. We don't know that one. That's what the probability of the intersection is 0.15. So what we're going to do is we're going to form an equation. Don't panic. Okay, so 0.65 is equal to, we're going to combine 0.35 minus 0.15. What would that be? That would be what? 0.20 plus x. Okay, how am I going to solve this equation? I'm going to subtract 0.20 from both sides. And that gives me 0.45 equals, these canceled out, x. What is x? This is the probability of B. Probability of B is 0.45. So it's just a matter of using this formula and then substituting in numbers and letters into this formula. Instead of using P, B, and all that, just put an X there. Combine the like terms, 0.35 minus 0.15, and then just solve this little equation. 0.20, you can even think of it this way, 0.20 plus what is 0.65? 45, huh? 20 and 45 give you 65. So you could just do it that way too. So let's try the one in the book here. They got another one. They have this problem. See, the probability of one thing happening plus the probability of the other thing minus the duplication, the intersection. This symbol is intersection. This is union. Looks like union begins with a U. Intersection is an and statement. This almost looks like an A. Okay. So the problem on this one is the person wanted to improve their cardiovascular fitness, and another person wants to lose weight, and they put them in this gym. But there's some people that probably want to do both. They want to lose weight and they want to want to improve their heart. So it said right here, according to this problem, they found that 70% of the people are concerned with either improving cardiovascular or improving their weight, losing weight. So 70% would be 0.70. The probability of people wanting to just do the cardiovascular kind of get in shape was 35%. So this is 0.35. The probability that some people just wanted to lose weight was 55%. But we want to know is how many people wanted to do both. They wanted to improve their heart and they wanted to lose some weight at the same time. So let's call that X. Okay, 0.70 equals, and then we're just going to add these together. What would that be? 0.90? Is that right? Minus X. So now I'm going to solve this equation. I'm going to bring this 0.90 to the other side. I'm going to subtract it off from both sides. But as you can see, 90 is bigger than 70, so this will give me a negative 0.20. There's more negatives than positives. And then here, well, this was a negative X. It had a minus inside. I can't just throw it away. But if I take the opposite of 0.20, I get 0.20, which would be the complement. And if I take the complement of negative X, I get positive X. So X is 0.20. So it's the kind of same thing. We're just substituting these numbers into a formula. Probability of the first thing happening, probability of the second thing happening, minus the duplication, the probability of the intersection of those two. All right. All right, let's see if we got one more that we can totally confuse you with. This one looks like a pretty hard problem. Okay, up here they have, let's see, maybe a little bit bigger. They have some kind of a chart up here. It says a survey of 1,600 customers comparing the amount of time they spend shopping on the internet per month with their annual income produced these results. And some of these people earned above, this person earned above $60,000. All these people earned above $60,000. Some spent 10 hours, 3 to 9, 2 hours, and then they totaled them up here. And 40 to 60,000, they took a survey of those people, at less than 40,000 survey. So when they added across here, across here, across here, then they added down, and this gave them a grand total of how many people were involved in this. This would be the amount of people, total amount of people that spend 10 or more hours, total people that spend 3 to 9 hours, 2 hours, or 0 hours, So what we want to do is find what is the probability that we randomly pick a consumer, just at random, and they neither shop on the internet 10 or more hours, nor they have an income above 60,000. They don't do either of those things. They don't make over 60,000, and they don't go on the internet 10 or more hours. So how could we even do this? Sounds kind of tough, doesn't it? Okay, so let's see if we can do. What we're going to do is just the reverse of what it says. T, we're going to just randomly use T. T, maybe I'll do this in a darker pen so you can see it better. T is going to represent the people that spend more than 10 hours or more on the internet. 10 or more hours. The reason we're going to do this is then at the end, we're going to find the complement of this. So these are people that spend 10 or more hours. And then A is going to equal the amount of people that have income above 60,000. See, they wanted just the opposite of this, but we're going to do just the opposite of what they asked us for. And we'll see how this works out. So, how many people spend 10 or more hours? 192, 160, and 128. We're going to add those up. 192, 160, 128. We're not going to add this because that is the total, 480. So 480 out of 1,600, this grand total right here, spend 10 or more hours on the internet, right? How many people are there above 60,000? All these people going across this way are above 60,000. They might spend less hours on the internet, but they all make above 60,000 going this way. So we're going to add all those numbers together. There's 192, 160, 176, excuse me, and 128. No, 128. And that adds up to a total of, what was that, 496 out of 1,600. So this is the probability of T. This is the probability of A. But if we just added them together, we get that answer. But we want to know where is the duplication. So this person right here is a person that they earn more than 60,000 and they spend more than 10 hours on the computer, 10 or more hours. They're doing both. This person doesn't qualify, although these numbers were the same. They don't qualify because they're not, it was just coincidental that they were the same. Because we want the people just that are above 10 hours and above 60,000. And what we want to do is we counted them here and we counted them again, didn't we? So we have to subtract off this 100 and Let's see if I got a little bit better pen. This one, hardly writing. We have to subtract off the 192 out of 1600. And that's subtracting off the probability of A intersect B. So if I use my calculator and I put this together and subtract this off, let's see what happens. I'm going to get 480. I'm going to turn this on, clear this out. 480 plus 496 minus 192 equals 784 out of 1600. And then what I'm going to do is change that to a decimal. So I'm going to take the 784 and divide it by 1600. Now to give me a decimal. And it comes out pretty nice, huh? 0.49. So is that my answer to the problem? Well, that is equal to the union of these two events, A union B. But we assume that these people spend 10 or more hours. We want to know the person that does not spend 10 hours, does not have an income above. So what we're going to do is we're going to use the complement of this thing. This should have been T intersect A. I guess I have the wrong numbers here. That's okay. We want the complement of T union A. We want the complement of that. So how do I find that? I take 1 minus 0.49. And that would tell us the people that, the selection of people that, the probability that we will pick somebody out of here. So 1 minus 0.49 is 0.51. And this will answer this question. Neither shops, this is the probability of picking a person that neither shops or has an income above 60,000. We have a 0.51, or you could say a 51% chance that the person we pick will fall into that category. Confusing? Well, don't let it get too confusing. So we figured out some problems here. I think we've got something going for us. And I think that's the only problem that we have left. Yeah. We're not going to worry about all this stuff. The explanation on this is a little confusing. So I thought I'd try to show you a little bit how they did it. Okay, how they got this number, how they got this number. So we added those together. And remember, when you're adding fractions, you only add the numerators. Subtract the numerator, get a new numerator, because all your denominators were the same. So you don't have to affect those. And then we just divided the top number by the bottom to get this number right here. Okay, so I hope this helps a little bit. Try some of the problems, and if you get stuck, ask questions. Okay, you can always ask me a question. We do have a live Zoom you can go on to, or you can request a live Zoom. So whatever it takes.